So our second student talk was unfortunately cancelled. So we will proceed to Gil Rosenman from engineering.
I don't think that I should introduce this remarkable person for thinking different, change the world, and putting in our pockets all well as an iPhone. Now we see everywhere, everything, and every second. Okay? And as far as you know, that next week, Tim Cook will visit Israel to open Center of Development of Apple in Herzliya with 800 engineers inside. Okay? And, you know, the main innovation which one of his saying is that the biggest innovation we should see in the newest time at the intersection of biology and technology. Let me add to this point that physics should be understood, and this is intersection biology, physics, and technology, I think really will lead us to new development, bio-inspired nanomaterials, which are composed from chemically synthesized biomolecules. So we try to use encoding of biomolecules and chemical synthesis to get something like new materials, or, as I was said one time, and I did not forget it yet, something even life. Not from two photons, Chaim, from these biomolecules. Okay? And today I will speak about bioorganic nanodots. Nanodots we do know about inorganic, and we will speak a bit. But nanodots bioorganic, which are composed from biomolecules, I will try to convince you that they are not only nanodots, small, with all kinds of physics inside, but also they are building blocks. You can use that in order to build different shapes, different morphologies, and different nanostructures, as it is done in our body. Inorganic versus bioorganic nanodots. First of all, everything in nano, when people understood that small is not only size but also a great physics. Started from E. Jima in 91, from carbon nanotubes, and then very soon with molybdenum selenide nanotubes done by Reshev Tenner in Weizmann Institute of Science. Okay? Now we are looking not only for physics, we are looking for new nanotechnology, new units which will allow to go bottom up to devices in order to use today's technology when 60 centimeter diameter silicon wafer is subdivided into small units in order to get small devices, all kinds of that you do know. And another development, I mean now silicon nanowires, okay? And another development is quantum dots, small inorganic dots, particles, which allow us to go to visible light. Red, green, and blue, for example, basic colors, and now from the January of 218 last year, the first TV based on quantum dots goes well by LG, Samsung, all large, huge companies now new TV with quantum dots, despite toxic cadmium. Okay? But if you are looking at this silicon nanowires or quantum dots, inorganics, all of them are single crystals. Atom to atom can build you these structures. And very strong covalent bonds or another bonds which make this single crystal very strong. And you cannot come back from these dots to separated individual atoms. By the way, all this development did not impress at all biological world. Even today, we start to think about nanomedicine, cargo molecules, and so on, and also dots inside our body to image all kinds of biological processes. However, I show you the example of, I show the example of elastic fibrils, which are the main component of our bones. I would like to remind you, we are perfect. I mean that the God did his job incredibly fine. And we cannot find inside our body or any other nature, I mean trees and around, any single crystals. Any single, it is completely different. I show you bioorganic dots which we found that are small homogeneous dots, about 2 nanometers, and it is the subject of today's lecture. Okay, we will compare between this inorganic and bioorganic, and I can say you definitely, and I greatly regret, nothing in common. What we have around in nature, we have nothing in common inside the world which we are going to develop.
One important common denominator, all invented by chemists. So we are talking physics and engineering, remember the chemists.
I agree with you utterly and completely. Okay? Despite that the physicists also supported this development. So on self-assembly from both sides. From this side, atom to atom, from this side, who can speak that biologists can talk with us on the level of atoms? Nobody. Because biologists know about amino acids, peptides, proteins, multi-atom structures. So the building blocks are not only building blocks, but units here and here are completely different. And the mechanism, physics of construction of this and this self-assembly is also different. Sorry about this. Okay. And building blocks. We will talk during all this lecture about building blocks. But anyway, if we are looking inside our body and the structure of all kinds of biological tissues, we will see a tiny scale, actin filaments, microtubules, and finally, human bone collagen K as example. You will see a tiny level multi-structural structures, multi-level, but there is no single crystal as we have, for example, in microelectronics. Okay? Finally, we are speaking about supramolecular structure. Nobel Prize 1887 by Len and two other scientists. When any structure in biology, and I will show you that binds by structures, okay? They are building blocks linked by weak non-covalent bonds. Weak bonds, reversible, dynamic, which allow us to see the evolution and which is provided by the nature, okay, to show how the evolution goes, because weak means it's not forever. You can break it, you can change, you can exchange building blocks in order to get different tissues or to improve them, okay? Now, let us speak about basic physics. Physics does work, but from another point of view, another pair of shoes compared to Haim. It was a great lecture, but I understood that we are from different sides, okay? Look at this, for example, nanotubes, which were produced by vapor deposition, developed together with Professor Gazit. You can see that these alanine dipeptide nanotubes have very definite cross-section. And it was a first point which I found that I understood, that I found a great thing. And great physics should be observed. About 150 years ago, this remarkable French scientist, Pasteur, told that the biological systems have a common basic feature, pronounced heraldic disymmetric structure. Asymmetry. This is the basis of biological world. In the inorganic world, we do know that any asymmetric structure has a definite and beautiful physical phenomena, which are described by asymmetric structure as I said, okay? If you are looking to the inside this inorganic world, you will see that we have unlimited number of crystals, different classes and so on, but most of them, I mean piezoelectric, 21 classes, asymmetric. It means that you can observe in these structures, if they are asymmetric, and biological structures, all of them are asymmetric. Basic physics, which is described by tensor of the odd ranks. I don't like to go into depths of these tensors, especially for people who are don't know about this. But anyway, I will show you two phenomena which you do know. Okay, the first one is piezoelectric effect. You apply voltage and you have deformation. Any AFM system, any optical system is governed by piezo. Everybody knows, even somebody who is smoking, when press, for example, on a piezoelectric crystal, he can generate a huge voltage and break down along the surface, and you can light your cigarette, okay? Piezoelectric effect. Another effect which is observed in a symmetric structure is nonlinear optics. Okay, nonlinear optics, when from omega you can come to 2 omega. Remarkable phenomena, very wide, and application are great. Okay, anyway, if it is so, we should find in any asymmetric biological system, and all of them asymmetric, between 20 amino acids, okay, only one glycine is symmetric. All other molecules asymmetric, and peptides, proteins, billions of them should demonstrate nonlinear optics and piezoelectric effect. Let's go with this, okay? Gorbitz from University of Oslo, he defined a space group and symmetry of dipeptides structures, and he found that overwhelming majority, or almost all of them, are asymmetric, okay? When we started to work, I would like to show you that, very simple, in a few seconds you can get that diphenylalanine hexagonal structure. You see remarkable cross-section hexagon, ideal, okay? It's nanotubes, which you can get from monomer molecules of diphenylalanine. Tetragonal, alanine, and LL orthorhombic. Dipeptide also, okay? All of them must demonstrate both piezoelectric and nonlinear optical effect, as well linear electro-optic effect, okay? We studied piezoelectric effect by piezo microscope and found that indeed both FF and LL do demonstrate strong piezoelectric effect. It is about 100 picometer of the volt. It's a high piezoelectric activity, and moreover, we found by means of simple rotation of the sample, you can see that what was bright and white, now after the rotation of the samples change the color to opposite, okay, means that we have spontaneous electrical polarization. Basic physics inside these bio-inspired structures, as well in LL, okay? Another phenomena of nonlinear optics, okay? We found that when we have FFF, tripeptide, and in different liquids, for example, in water and chloroform, we can get or belts as the belts or these spheres. Both of them are demonstrate strong second harmonic generation. Moreover, we found that for both of them, I mean, especially for this one, we have strong orientation of molecules, of building blocks, I mean, spontaneous polarization along the main axis, okay? Now, you can see a picture. The upper one is normally standing peptide nanotubes, okay? And second one is propagation of fundamental frequency when you illuminate from the back, okay? You can see that the light propagates along the hole inside these nanotubes. And the second harmonic propagates inside the walls. Okay? Finally, if it is so, we found how to use it for frequency doubling and radiation illumination by 1.6 micron led to second harmonic generation and green light using this FFF peptide nanostructure. Okay? Let's come to nanodots. Okay? You can see one of the pictures which I like, because you can see here supramolecular structure atom. You have building blocks which are self-assembly into nanostructure. That is exactly what is going on. From two molecules, two photons in your language, okay, we can get a small baby from two molecules, and after this baby begins to grow inside man, we're outside, and after this, it can come to human being. Perfect creation of nature. We hear, we see, we feel, we talk, we think. Amazing. Self-assembly. Okay? Now, how is going on? Look. At the first stage, these simple building blocks, dots, ring. After this, they are self-assembly in a liquid. You should provide this liquid in order to get specific shape, morphology, and properties. And you see here, finally, we have nanotubes, fibers, whatever, okay? But what is important? Supramolecular structure. Supramolecular structure like this one, you have building blocks, and between them, weak, reversible, dynamic bonds, okay? And the idea, which I will show you how it's going on, is to use the weakness to break these bonds, and you will see, you will get what? Nanodots. Building blocks of this supramolecular structure. How is going on? You can see that we have, as a result, two-domain structure, building blocks and these connections, links. They're completely different. Chemical composition is different, and the properties are different. Okay? Let us go further and show how we can find these building blocks. Okay? The first pioneer in the field was Professor Gadiri from US. He used completely it is biological structure, but you can find it in the human body. It's eight amino acids and this cyclic peptide. He put in these molecules into the water and found these nanotubes. It was the first publication. After this, you will find, I don't know, hundreds of thousands of papers on different peptides, molecular proteins, and so on to make bind-spine structures. But from the very beginning, he told that any structure, because they are supramolecular, are based on these building blocks. And he told that each building block, each is composed from two molecules. From two molecules. It's amazing. And they molecules, and these building blocks, okay, are connected by hydrogen bonds, specific bonds. Not all bonds which are link building blocks, hydrogen bonds. There are many, many, many other, but this one, hydrogen bonds, okay? But what do we know about this? Nothing. Nothing. Until now, there are only few people who were involved in studies of physics of these building blocks and physical properties of the bio-nanostructures, okay? We used two different techniques to get these nanodots. The first one is top-down. Let us take these nanotubes and dissolved and disassemble to break, as I said, uses hydrogen bonds, weak bonds between building blocks, and you will see nanodots, okay? Another point is related to bottom-up. We start from monomer molecules, okay? And at a definite stage, we can come to building blocks which are self-assembly at the third stage to nanotubes. Sincerely, it is a multi-stage process. But anyway, the first one is monomer and then building blocks, and after this, arrangement of self